to circuit element. So let's talk about the different elements could be involved in the circuit. First one is the independent sources. We have two types of independent sources, voltage source and current source. So to voltage source, which is represented like this in the circuit, obviously the positive and negative polarities are labeled here, very nice. And the voltage source is able to guarantee the voltage between these two nodes, A and B. While the current through it, no matter what is the current direction, is really depends. It depends on what? Depends on the rest of the circuit. In other words, the independent voltage source can guarantee a voltage between these two nodes, two terminals, no matter what is the rest of the circuit. It doesn't care. However, the current through this voltage source depends on the rest of the circuit. Okay, so it will be safe for us to say that the independent voltage source current is something we don't know at the beginning. And by labeling here, we can tell easily the voltage value. However, the current, we don't know. Same thing for the current source. Independent current source can guarantee the current flow through this branch. However, what is the voltage between these two terminals A and B? We don't know. It's all depending on the rest of the circuit. Okay, so we can safely say we don't know the voltage across A and B here until we analyze the entire circuit. Okay. So only current value is given and labeled here. Next is dependent sources. Now we have two types of sources, voltage or current, and also we have two dependency, either voltage dependent or current dependent. Therefore, we have up to 4 types of dependent sources. First of all, let's take a look at this one. So by the symbol here, we can tell this is a voltage source with positive and negative polarity labeled. The voltage source voltage value is equals to a function in terms of another voltage. So we can tell this is a voltage dependent voltage source. Okay. And the second here, by the symbol here, we can tell this is a current source. And the current value is equals to something in terms of another voltage. So this is a depending on another voltage current source. So voltage dependent current source. Third one here. Again, this is a voltage source. And its voltage value is in terms of another current. So this is a current dependent voltage source. Last one. Current source, first of all. And then what is the current value? Depending on another current. So this is a current dependent current source. So same as the independent sources, we can guarantee the voltage for voltage source or guarantee the current for the current source. However, what is the current of the voltage source? We don't know. What is the voltage of the current source? We don't know either. All right, continue our circuit elements. Let's talk about R, L, and C. They are the most commonly used elements in the circuit, and we are quite familiar with their circuit symbols. Okay. For resistor, we have kind of a sawtooth look, and inductor, we have a curly look, like coils, windings, and to capacitor, we have two parallel bars perpendicular to their two terminals. And of course, one of the bars could be curly. To resistor, the resistance is represented by capital letter R, and unit is ohm. And resistance value equals to the voltage across it divided by the current through it. This is nothing but Ohm's law. And to calculate the resistor's power, we again apply the relation we learned from previous slide, product between voltage and current. And we can also substitute VR by IR times R. We end up with this power equation. Similarly, we can substitute the IR by VR over R. So we end up with this power equation. Okay. Second, inductor. Inductor has inductance L in unit of Henry. And the voltage of the inductance is equals to inductance value times derivative of the current through it with respect to the time. The equivalent equation is actually to derive the current out of this equation. So the current equals to 1 over inductance times integral of the voltage. So these two equations are equivalent, pretty much expressing the IV characteristics. The power remaining same as product between voltage and current. Last, E is what we learned, energy. Right? The energy of the inductor is equals to half product between inductance and current square. Here it is noticed that both inductor and the capacitor are called energy storage element. So they can store the energy. And the stored energy is following this formula and this formula, respectively, for inductor and the capacitor. So speaking of the capacitor, capacitance C in unit of farad. Here I want to emphasize the unit, or say the importance of the units. They are not only telling you the magnitude or say the size of the element, but also telling you which element it is. Okay, Henry, when you talk about, is definitely inductance. Farad, when you talk about, is definitely a capacitance. Okay. IV relations like these. So the current of a capacitor is equal to capacitance times derivative of the voltage across it. Okay, it's not like the inductor here. This is the voltage equals to inductance times derivative of the current for inductor. Okay, this is different. And equivalent equation is the voltage of capacitor equals to 1 over capacitance times the integral of the current. Power relation remaining same. Some real RLC pictures here. First of all, let's talk about the resistor. So resistor, what are you seeing here are different resistance value, of course. However, more importantly, from the size and the look, we can tell they are having different power rating. Look at these guys, very small package used in our labs all the time. Okay, they are having much smaller power rating. By that, it means 1 kilo ohm used in 1 kilowatt application or 10 watt application is completely different resistor, even though they have same resistance value. So from the look, you can tell these are obviously high power application resistor. A little bit more about the lab use resistors like these. Their power, generally speaking, is either quarter watt or half watt. And also another thing about the resistance is most of the resistance are temperature dependent. Okay, this is a non-linearity of the resistor, which need to be taken into consideration when you have a design. Next, the inductor. The inductor is as simple as a coil winding onto a core. This core has different types of material. And then two leads out here and here. They are two terminals of the inductor. Okay. And then last, the capacitor. You have bigger ones, smaller ones. The difference is not only the capacitance value, but also the voltage ratings. So resistor has power rating, the inductor has current rating, and the capacitor has voltage rating, in addition to their resistance, inductance, and the capacitance values.